we're going to be talking about linear models and how do we actually, or any kind of modeling is what we're going to be doing in this chapter. And modeling is where we come up with a kind of an equation and then we solve that equation. In this case, we're going to be coming up with different equations. And we're going to first talk about linear models. So there are lots of other types of models you can have. We're going to first look at growth and decay. There are other types of linear models we can have. And what a linear model for growth and decay is about is that the rate of change of your population is actually proportional to the size of the population. So we have this equation of dp dt is proportional to p, where that symbol there means proportional to. And what we want to do is try to figure out how we come up with this. Well, unfortunately, this symbol doesn't help us very much. So we want to try to come up with an equation for this. It's going to be a differential equation because we're involving a derivative. And it turns out that if we just throw a constant in here, we can actually get the differential equation. So dp dt is equal to some constant times p. We can have an initial value. So p of 0 equals p0. That's what we started with. And we can solve this differential equation. So let's see how we solve this. So dp dt equals kp is our differential equation. Again, we also have the initial condition of p of 0 equals p0. So let's talk about how we solve this. Well, one of the things we're going to notice is it is in fact separable. So 1 over p dp is equal to k dt. And then you just take the integral of both sides. So we end up with the natural log of p, of the absolute value of p, is equal to kt plus c. We take the integral of both sides. We want to solve for p, get p by itself. So we'll first raise both sides, e to both sides. So the absolute value of p is equal to e to the kt plus c. That would be the absolute value of p is equal to c e to the kt, because you get e to the c and e to the c is just a constant. And then that constant can take into account the absolute value. So we can actually say p is equal to c e to the kt. Again, we have that initial condition. So p of 0 would be c e to the 0 is equal to p0. And that implies that c equals p sub 0. So p of t is equal to c, keep doing that, is equal to p0, because we now know c is equal to p0 e to the kt. And this was a differential equation or an equation that you dealt with in algebra all the time. We now know where it comes from is this equation here. And it basically allows us to see how they relate and where the equation came from. Let's talk about whether we have growth or decay. So let's talk about k is positive. If k is positive, then you have e to the positive kt, and we know from algebra that that looks like a graph that looks like this. That means it's always increasing, and that means we have growth. If k is negative, then you have p0 e to the negative kt, basically, because k is negative. So you have a negative exponential, and that looks like this. And we know from calculus, actually, that this is always decreasing, and so therefore we have decay. So let's take an example of this. The Shroud of Turin, which shows the negativity of the body of a man who appears to have been crucified, is believed by many to be the burial shroud of Jesus of Nazareth. In 1988, the Vatican granted permission to have the shroud carbon dated. 3 independent scientific laboratories analyzed the cloth and concluded the shroud was approximately 660 years old and age consistent with its historic appearance. Using this age, determine what percent of the original amount of carbon-14 remained in the cloth as of 1988. So again, we're looking at something that's would be changing. The rate of change would be proportional to how much we actually have. So we know that we have dp dt is proportional to p. And we know this because time does not evolve in this when something is decaying. If something is decaying or growing for that matter, it's just going to be related to this. So we know we have dp dt equals kt. We also know that p0 would be P of 0. All right, P, by the way, is the amount. So we didn't need to use P, we could have used a different letter, but we have the amount of carbon 14 at time T. And so we have that. In fact, I could even write this a little bit differently. Instead of calling it just P by itself, I'll call it P of T is equal to the amount of carbon 14 at time T. And again, you could have used A instead of P. You can use whatever letter you want. As long as you define your variables, it doesn't really matter what letter you use. All right, so again, this is a separable differential equation. So we take the integral of both sides. And we already know what this is, but we're going to do it anyhow. This would be P. This would be 1 over, whoops, I need to separate it first. So let's separate it first before I take the integral of both sides. So we have, and I wrote this wrong. That's why I thought it was separable already. It is dp dt equals k times p. I don't know why I wrote a t there. So 1 over p dp is equal to k dt. Again, then you take the integral of both sides because it's separable. And we end up with the natural log of p is equal to kt plus c. So p is equal to c e to the kt. And then p of 0 is c e to the 0 equals p0. That says c equals p0. So we now know that p of t, and we already knew this, but we went ahead and solved the differential equation at 10, is this. But the problem is we have too many parameters. We don't know what p0 is. We don't know what k is. We got to find both of these. So we're going to use something we do know. We do know that carbon 14 has a half-life. So if we can find the half-life of carbon 14, and this is actually known through experimentation. We do happen to know what this is, and this is actually equal to 5,730 years. So what that means is in that time period, half of what you started with is left. So P of 5,730 would be half of what you started with, and we started with P0. Okay, so we can use that idea. If we have half of what we started with, when T is equal to 5,730, we would be able to solve this equation and find K, because the only thing we don't know now is K. Notice your P0s would cancel from both sides of the equation. So 1/2 is equal to e to the 5,730 times K. Take the natural log of both sides, and you now know what K is. So K is equal to the natural log of 1/2 divided by 5,730. So we now have that P of t is equal to P0 e to the natural log of 1/2 over 5,730 times t. All right, so now we're looking at that information, and we want to still know how much was left. Let's go back to what we were trying to find. We now have our equation for this. We want to use this to determine what percent of the original was left as of 1988. We are told that this 660 years old. So we are told that T is 660 years old. So we're saying T is 660. So you're just going to put in 660 in for T. So now we take out our calculator, because at this point, we're not going to do this by hand, and find out what this is equal to. Notice I didn't find an approximation for K until now because I didn't want to cause rounding errors. So this is a good idea to do. So we just have to figure out what this is and get an approximate answer. And the approximate answer is 0.83. Let's call it. And that's, we don't know what P0 is, but all we want to know is what percent was left. So P0 is how much we started with. And then what we're left with is about 83% of what we started with. So left with 83% of what you started with. And this is how they do carbon dating, is they actually look to see how much, what percent is left, and from that they then can extrapolate back to find out what time it was. All right, so now let's look at some other models. Let's look at harvesting. So this is one, you were dealing with equations like that before. Now we're going to look at harvesting, and harvesting is still kind of the same idea. It's still about growth and decay. So we still have our slope is still going to be, our slope of our tangent line is still going to be proportional to P, but then there's going to be what we call a harvesting factor. So this is how much is being taken away. So dp dt is equal to K times P minus that harvesting factor. So we're growing by Kp, but we're then taking away some of it. And we want to look at how we solve these. So now you're going to notice, first off, this is not separable. And in fact, it is actually linear. If you notice, if you took the dp dt and you subtracted the Kp from both sides, you would see you actually have a linear equation. And we can then solve this linear equation. I'm not going to solve it in general. We're going to just usually solve these every time we have a problem, but that's what you would go through and do. By the way, you can also do where things are added to it. So you could also have another factor where we're actually having added to it, where you're like stocking the pond, or you're having immigration into your area. This actually is very good for looking at immigration and emigration. So you could have H not being a harvesting factor, but how many people leave, and then you could have another factor of how many people come in. All right, so we have that equation, and then you just solve this differential equation, nice little linear differential equation. Another application is Newton's law of cooling or warming. And this is, we've seen this in some group works, but you also can think of this as your rate of change of temperature is actually proportional to the difference between the temperature of the object and the temperature of what we call the medium. So if you put a cold glass of water in a warm room, then if you think about it, the farther away that cold glass of water is from the temperature of the room, the faster it's going to be the rate of change. And then as the temperature gets closer and closer to the temperature of the room, then the rate of change will actually be slowing down. And that's why we say it's proportional to that rate of change. So T is your temperature at some time T. T sub m is the temperature of the medium. And because it's proportional, we just throw in that proportionality constant. So here's our differential equation that we want to then solve. So let's go ahead and do this one. I didn't do the last one, but it's basically the same kind of idea. We're going to go ahead and multiply out. So we have Kt minus Kt sub m. T is your variable. T is your dependent variable, sorry. Tm is a constant. It's your temperature of the medium. Now, in reality, the temperature of the medium is in fact changing slightly from that object. So if we're cooling something down, if the room is cooler than where you were, like you put something in the refrigerator, the object, if it's warm, will actually warm up the refrigerator a little bit. This is why they say don't put really warm things directly from the oven in your refrigerator, because it will warm up the refrigerator. But the change isn't as big as it would be for the temperature of the object. So we're going to simplify it by not worrying about the temperature of the medium changing. But in reality, it does change a little bit when you do that. And it's usually just around the object. It's not the whole medium that might be changing, but it does change. So it makes it a little bit more complicated differential equation. We will simplify it and again, assume that T sub n is constant. So this is also, if I bring that KT over to the other side, I get a nice little linear differential equation. So we're going to go ahead and solve this. My integrating factor is equal to e to the minus the integral of minus k dt. So it's going to be e to the minus kt. So we're going to multiply that through. So e to the minus kt dt dt minus e to the minus kt times kt is equal to e to the minus kt times minus kt sub m. Again, this is your derivative of your integrating factor times your dependent variable. And then here we have minus kt sub m e to the minus kt. And then you just take the integral of both sides. So the integral of a derivative is, of course, the thing inside. We've solved these before. This isn't something new. And the integral of this would be t sub m e to the minus kt plus c. You could then solve for big T. So big T would be t sub m plus c e to the kt. I should mention that the temperature at time 0 is T sub 0. That's what the object starts with. So that's what temperature it starts. If you have a warm temperature or so forth, that's the temperature you start with. All right, and so you can therefore find out what C is. And it becomes a little bit more complicated, so I'm not going to go ahead and do that, but you can solve for that. It's not too bad. So let's check an example. A thermostat is taken from an inside room to the outside, where the temperature is 5 degrees Fahrenheit. After 1 minute, the temperature reads 55 degrees Fahrenheit, and after 5 minutes, it reads 30 degrees Fahrenheit. What was the initial temperature of the inside room? So that's our question. So we actually want to know T of 0 equals T0. We want to know what that is. Again, we have that dt dt is equal to k times t minus t sub m. And so we have this equation already. We've already been dealing with it. We already know the solution. If you want to, you can solve it again. It's not going to change any. So we already know what this solution is. If we go back here, we can look to see what we had. And we had this equation. So I'm going to go ahead and just remind myself what this equation is and bring this over where I am. But again, you can solve this again. It's not like you have to memorize this. It's just solving this differential equation. And we already know how to do that. So we can do that. And let's say we did that. So we solved this differential equation. Here it is. And here's my equation. And now what we have to do is try to figure out how do we find out what these parameters are? How do we find out what K is? How do we find out what C is? How do we find out what the temperature of the medium is? All right, so we know the temperature of the medium because that's the temperature of the outside. So the temperature of the medium happens to be 5 degrees C. I'm sorry, 5 degrees F. We know that after 1 minute, the temperature reads 55 degrees Fahrenheit. So we know T of 1 is 55 degrees Fahrenheit. We know that after 5 minutes, it's 30 degrees Fahrenheit. So T of 5 is 30 degrees Fahrenheit. And so we can actually put this information in. T of 0, we don't know. We don't know what that T0 is equal to. That's what we're looking to find. T sub 1 would be the temperature of the medium, which was 5 degrees, plus C e to the K, which we don't know K, times 1, which we do know time, and that equals 55. Okay. So that gives me that CE to the K is equal to 50. We also know that T of 5 would be 5 plus CE to the 5K, and that equals 30. So CE to the 5K is equal to 25. So we have 2 equations and 2 unknowns, and we need to find out what both those pieces are. So we can actually do this quite easily. Just solve one equation for one variable and stick it into the other. So e to the k, actually we'll do it this way. C is equal to 50 over e to the k. So we can plug that in. 50 e over e to the k is equal to e to the 5k equals 25. So that means 50 e to the 4k equals 25. So e to the 4k is equal to 1/2. So 4k is equal to the natural log of 1/2. So that tells me that k is equal to the natural log of 1/2 divided by 4. We actually want to know what c is. So c is my time of 0. So actually it might not be. Let's keep going. So let's find out what c is. So c we already know is 50 over e to the k. So c equals 50 divided by e to the k, and we just know what k is. So we can find out what that is. And I'm going to go ahead and approximate what that is. So we have 50 divided by e to the natural log of 1/2 divided by 4. Oh, can't type things in right. Sorry about that. And 50 divided by e to the natural log of 1/2 divided by 4. Okay, I just can't use my own calculator. And so we get that C is equal to 59.4604. Now that may not be, that we don't know what that is, what our initial condition is yet. So we can now put all this into our equation. So T of t is equal to, going back up to our equation, T sub m plus C e to the kt. So T sub n plus C, which we found out C was 59.4604, e to the kt, and k we found out to be natural log of 1/2 divided by 4t. So at time 0, T sub m and that's going to equal the temperature of the room. Or our initial temperature, we'll just call it the initial temperature. We actually already know what the T sub m is. I forgot we knew that. That's 5. So we can actually now find out what T sub 0 is. So just by taking this and simplifying this, I don't need a calculator for this because e to the 0, of course, is 1. So then T sub m was 5. So 5 plus 59 is 64.4604 degrees Fahrenheit. So the temperature of the room is 64.5 degrees Fahrenheit. All right. We can also talk about mixtures. You've actually done some mixtures before, possibly. And so mixtures are the amount of salt at time t. And in this case, the rate of change is equal to the rate in minus the rate out. And this makes sense. You're pouring something in, you might be taking something out, and that would be what your rate of change would be. This is really difficult to try to write in general. So I'm going to go ahead and just do an example of this. So a large tank is filled to capacity with 500 gallons of pure water. Brine containing 2 pounds of salt per gallon is pumped into the tank at a rate of 5 gallons per minute. The well-mixed solution is pumped out at the same rate. Find the number of pounds of salt in the tank at time t. Now, the thing is that we don't really care that much about this exact problem, but we want to talk about brine is probably not of importance to you, but brine could be anything. It could be a pollutant. It could be any other topic or substance you're pouring into it. And we want to talk about what this would look like and what would this be. So first off, we are looking for the amount of salt at time t. So A of t is the amount of salt at time t. And again, you can call this anything you want as long as you define it like this. Make sure you tell people what it is you're dealing with. Okay. We need to figure out what is my rate in. So my rate in, if I come up here, is it's being containing 2 pounds of salt per gallon is being pumped in at a rate of 5 gallons per minute. So I want to look at, I use units a lot to help me with this. So remember, I'm looking for dA dt dt, and that's my rate in minus my rate out. So looking at this, dA is going to be, A is going to be in number of pounds, so it's going to be pounds, and T is in whatever time happens to be. We look like we're looking at minutes, so it's going to be pounds per minute. So I need my rate in and my rate out to also be in pounds per minute. If I notice this, I have a rate in of 5 gallons per minute, but that's not in pounds per minute, that's gallons per minute. So I use my units to help me with this. I have 2 pounds of salt per gallon. So I also know that I have 2 pounds per gallon. And I look at my units and notice that my gallons will cancel and I'll be left with pounds per minute. So I find out it's 10 pounds per minute is my rate in. I'm then going to look at what my rate out is. A well-mixed solution is pumped out at the same rate. So my rate out, in this case, is being pumped out at 5 gallons per minute. If it's not being 5 gallons per minute, if it's not the same rate out, then you'd have to do some work to figure out what that would look like. But we know it's 5 gallons per minute, but we have to look at what is being pumped out. We know 2 pounds per gallon was being pumped in, but we don't know how much is being pumped out. But we do, because A of t is the amount of salt at time t. So we know that dA dt, or A of t, over, it's going to be your pounds per, now how many gallons? Well, we had 500 gallons of pure water. So we had 500 gallons in this tank. At this point, at A of t, there's no longer 500 gallons of pure water, but there still is 500 gallons because we're taking rate in and rate out the same. So this is where if your rate out was different than your rate in, then it wouldn't be per 500 gallons. It would be per 500 gallons minus or plus whatever that rate, that change would be of your amount of liquid. But in this case, it just happens to be just per 500. So we still get pounds per minute like we wanted. So we notice we have A of t over 100 pounds per minute. Okay, so we now have a rate in and a rate out. So my dA dt is my rate in, which was 10 pounds per minute. And then we're going to subtract off my rate out, which we now know is A of t over 100. At time, we do want an initial condition. So at time 0, how much salt was actually in the tank? So we come back up here and we notice that it was filled with pure water. So at time 0, there was no salt in the tank. So at time 0, the amount of salt in the tank was 0. And now you notice this is a nice linear equation. You know how to solve this, and we can now solve this. I'll let you solve this on your own, but that's basically what you do. One last example is a series circuit. This is known as a series circuit. So what a series circuit is what we're going to have an energy source. We're then going to travel from that energy source. We usually think of having an arrow here to tell us what direction that energy source is traveling. In this case, this is going to go through an inductor. An inductor actually saves the current. And it's going to go through a resistor, and that actually takes away some of the voltage. So we have a voltage drop across the inductor where it's changing the current, saving some of the current. So we have the size of the inductor, that's what the L represents. And then dAdt, because it's saving some of the current is changing. So we have a rate of change of the current over time. And we call that the voltage drop because that's going to take you how much the current is changing times the how much the inductor is. The voltage drop across the resistor, again, some of the current is being taken away, some of the voltage is being taken away, and it's by how much the current is times R. And E of T is just how much voltage you put into the system. Kirchhoff's laws tells us what the differential equation would look like with this. We come through E, so we add this, because that's voltage being put into the system. We then are taking away some of the voltage, because we have a voltage drop, so it's going away as we come through the inductor. We also have a voltage drop through R, so some of it's going away as it's coming through the resistor, and then we're back to our voltage source. So we end up with E of T minus the voltage drop through the inductor, minus the voltage drop through the resistor. Back to where we started means we get back to 0. Because Kirchhoff's law tells us that as you go around a closed circuit, you will get to 0. So we now have this differential equation, getting just putting the derivative on one side, the I on one side. E of T is constant in terms of I. It's not constant in terms of T, but it's constant in terms of I. So we'll take it to the other side. Again, we get a nice linear differential equation. And you can solve these.